Wow. I am glad we got that captured on video. This is going to be fantastic. I think we have a new #1 rated video coming up here. We're open for questions now, and we'll try and keep it to about 25 minutes. And
hello? Can you hear me?
Yeah.
Okay. So 3 questions. Hopefully you will get addressed either right away or as you talk about things.
Okay.
My car. How much is a battery like this going to weigh to put in my car?
So the battery weight in a car by the automotive engineers is roughly got to be about 30% by mass total. So I got to work it backwards because, you know, if you want to get a longer range, we just put more battery. So if we made the car 90% battery, there's no room for you. So the sensible amount is 30%. So you figure, you know, car weighs about, what, 3,000 pounds, so 30% is 900 pounds. So
that's a lot of battery.
yeah, it is.
Okay.
It is. But it's not the issue. The issue is what's the capital cost? If I can, you know, if I can put a car on the showroom floor for the same cost as the internal combustion engine, and you know that that battery isn't going to poop out the way your cell phone battery does, you'll buy it.
And if my weight is on the bottom, then I'm not top heavy.
No, of course not.
Okay.
You have better handling.
Second question.
Yeah.
When is this going to be available for my house? Right now I have a generator to get
Okay.
me through the next Ike.
So we hope to release our first product about a year from now, and that's going to go to military bases and so on. It's got to be, this is a game, one strike and you're out, okay? If anything goes wrong, we will be destroyed. You remember that guy, actor, he was in Fast and Furious, and he was in a car accident with his buddy, and they smashed this tricked out Porsche into a tree, and it burst into flame, and they were both killed. I read the reports. Not one drew attention to the fact that that car burst into flame. If that had been an electric car, that would have been the lead headline. Whoa, look at that, electric car catches fire. So that's the burden that we have to bear. It's, you know, you've got to be perfect. So answer your question, 5 years. 5, not 25, 5.
And last question.
Yeah.
Clearly you've made a lot of investment, a lot of money.
No, I haven't made any money. There's no money.
No, presume people put a lot of money into it.
Well,
I
people-
expect you want to make money back.
Yeah.
How are you protecting your investment from someone who says, ooh, I saw this cool lecture, let me go steal that, make it offshore, and sell it for less money?
So that's always possible. That's always possible. So you have intellectual property, which is your protection that if somebody invades your market with your product, you have the right to and join against them. But there's nothing to stop anybody. I mean, you can read my papers. If you read my papers, I lay it all out, right? But there's more to it than is there. You know, they can cut it open ultimately. And they will. You know, but you know, if we want to just get blunt about this, if we're worried about somebody in China copying this, China's a big market, and the strategy there is to have a Chinese partner. I think that's all going to come to an end pretty soon. You know, for the first 20 years after the fall of communism, it's really funny for people in former communist countries to be stealing from the rest of the world, ha ha ha. But eventually, as their own indigenous wealth grows, and they start stealing from other wealthy indigenous people, they're going to go to the government and say, that's enough of this. So I'm not worried about that.
Professor, terrific presentation. A couple of questions relating to Tesla, since you mentioned the gigaplant, the factory. I don't know if you've actually been to a Tesla and actually seen the chassis, drivetrain, the induction motors, and battery frame. But you know, it's weight balanced, about 51% on the rear and 49% because the battery jacket is underneath the car. Do you envision a battery adaptation for your battery and this sort of the same thing where it would be underneath and it would be more like the cells where they have the liquid cooling, liquid cooling jacket running through the vehicle to dissipate the heat? Is that the anticipation in your model in the event that your battery is adopted for an automobile?
Yeah, I don't care about the design. The design is free for the automotive people to figure out how to best incorporate it. So it's really agnostic on that.
Okay, as a follow-up, you mentioned the magnesium and antimony. Assuming that in the future, 10, 15 years out, there's wide adaptation of your technology on a worldwide basis, do you anticipate any issues with the price of those two commodities rising pretty dramatically just because there would be all of a sudden a big shift in the demand, with the adaptation?
Yeah, it's, first of all, we looked at earth abundance, and it's a chicken and egg situation here, that the world supply of antimony right now is what it is because it satisfies the demand. If the demand grows in a sensible way, then at some point you could open up more mines. I mean, we saw this in the late 80s when nickel metal hydride batteries came into being, and that was what gave us the first laptop computer. You know, we could have built a laptop in 1985. We had everything that we needed except a decent battery. If we put a lead-acid battery in a laptop in 1985, it would have run, maybe 1 hour, so it wouldn't have been worth the effort. But with the advent of nickel metal hydride, that triggered the opening of new nickel mines. And there was some rocking of price, but it didn't go. It's not like what would happen with platinum. If all of a sudden fuel cell vehicles came into being and everybody needed, I don't know how many tens of grams of platinum per car, I mean, it just doesn't exist. So I don't see that. But the other thing I wanted to point out is that, I talked about magnesium antimony, but then the Nature paper is lithium with lead antimony. And so I can put antimony on the bottom, lead on the bottom, tin on the bottom, bismuth on the bottom, alloys of all of the same. And so at one point I was calling an antimony producer. There's a company up in Montana or someplace. I'm from Canada, I don't know, someplace out west there, but anyway. So I called him up and I said, so talk to me about antimony production and your process and whatnot. And I asked him about purity and cost. And I said, well, what's one of the main impurities? He said, lead. Well, I'm doing lead antimony. I said, well, what if I don't need to remove the lead? Oh, he says, you don't need to remove the lead. Your price goes way, way down. And then I call a lead guy and I said, what about the lead? Oh, one of my main impurities is antimony. And see, people don't think about supply chain that way. And I call a lithium guy. I call this guy I know in Germany, where they have a smelter. I said, what's your main impurity in lithium? He says, sodium. Well, sodium in our cell is fine. So, people who are doing these cost models, they're doing the cost models on, reagent grade stuff. And so I'm not worried about that at all. But in anticipation of it, I'm also working on electrolytic production of metals. So I know how to produce them too. We should just go and just put the smelter right at the mine site and build the batteries. I mean, why not? I mean, why ship tons of dirt to make pounds of metal? Why not take the factory that's about the size of that assembly plant I showed you would fit into this corner of the room, and I've got an electrolyzer that would, something half the size of this room would just put it at the site. So that's a way to think,
If you're not cycling the battery continuously like you would be with a wind farm, what's the cold start time for a battery if it's been turned off and allowed to cool?
So cold start time would be on the order of 3-4 hours, something like that. And if you didn't cycle them on a daily basis, that 53-foot shipping container would take 3-4 days to solidify, and it would solidify from the outside in. And as long as you've got some cells in the center that are still molten, once you start passing current, then they'll generate the heat and melt back out. So it's not as though it's all or nothing. It's not an isothermal system.
On your smallest cell that you've made, what's your specific capacity?
The smallest cell?
Energy density, gravimetric energy
Oh,
density.
gravimetric energy density is about 50 watt-hours per kilogram. It's very poor. And that was the courage to be able to say, don't allow yourself to be dissuaded by a poor gravimetric energy density because it's not moving. But if we go to the displacement battery, it'll be 150, which is comparable to lithium ion. So if I can give you a lithium ion energy density at lead acid price point with an infinite lifetime, I'll put everybody out of business. But when you're talking about stationary, it boggles my mind. Once in a while, I've stopped going to a lot of these conferences, but I'll go to a conference and there's people at the screen and they're showing gravimetric energy density for stationary storage. Well, who cares? It doesn't matter. But people look at it and say, yeah, his voltage is low. Doesn't matter. If you want 300 volts, I just number them in series. Oh, but his temperature's high. It doesn't matter. All that counts is dollars per kilowatt hour. Don't get, so they say, safety. That's another one. I had a couple of DARPA guys visit me about 4 years ago. And they said, could you put one of these things at a forward operating base in Afghanistan? I said, yeah, sure I could. He says, can you give me something even better than magnesium antimony? I said, well, I can give you a 2-volt system like that, but it's very expensive. He said, I don't care about cost. I'll build you a lithium tellurium. It's a 2-volt system, and it screams. His buddy says, yeah, but what happens if a sniper's bullet shoots into the battery? I said, well, if it goes in the top, it'll alloy with the upper metal. If it goes in the bottom, it'll alloy with the lower metal. He said, yeah, but what happens when metal leaks? I said, it'll freeze. They look at each other and say, battle hardened. So you see, it's counterintuitive. Everybody thinks a room temperature battery is safer. No, it's not. If a truck flips over with this thing, you got salt on the road. We need that in Boston. Who cares, right? But if you've got a truckload of lithium ion batteries, and that thing flips over, and those cases crack, and now you've got the liquid everywhere, which is flammable, as in the case of Le Flameliner, right?
Well, it's kind of interesting that you talk about Flameliner, but I'm sure there are a lot of gasoline engines which are caught on fire.
That's right.
The jet fuel engines which are caught on fire.
That's
on
right.
airplanes too. So anyway, my question was about how fast can you charge and discharge these batteries?
Oh, we can charge and discharge them very, very fast, but it's not efficient to do so. So if you need to, if you want to use them as an instant load, for power, the power you can design for that, but these are not designed for, like, we could use them for frequency regulation if you want. This could be playing in multiple, you can superimpose electrical signals. So this thing could be doing a slow discharge, get a signal from the grid, and all of a sudden do frequency regulation for I don't know, 10 or 15 minutes or something like that. But the design specs that we were given, we talked to a lot of potential customers, and we were led to believe, look at 4-hour charge, 4-hour discharge, and then, 8 hours in between rest and stuff like that. But, some people want 3, some people want 5 hours. But you could use it for jackrabbit starts, but you'll generate a lot of joule heat. Your efficiency will be low, but if you needed it for a short burst, you could. But, I've talked to people about combining this with ultracapacitors to give the short burst.
Okay.
But,
Excuse me. One question, since there's the usual problem that this is DC and everybody's AC, what's your overall efficiency on the systems as you've come up with, that you're marketing right now? How does it compare to some of the other battery systems out there?
It's comparable to all the others. The same issues exist for all of them in terms of the inverters that are out there are really good for high voltage, low current, but these are low voltage, high current. And I don't know enough about the electrical engineering to tell you whether that's intrinsic or it's just there's been no demand, and so people haven't really tried to design them. But I'm not worried about that. The ancillary electronics are the same across all platforms. Right now, What we're tasked with is putting together the cells that will operate with a long service lifetime at a low capital cost, and then you got that interface.
I was just wondering how much of the energy is converted into heat. So what's the efficiency of the process?
That was the 75% I was saying. 75. So I think it's about a little over 20% is converted into heat, and desirably so.
My question is, what is the biggest stumbling block in reducing the form factor of your battery? That's the first question.
Well, it's not a stumbling block. It's a law of nature that if you make the battery too small, it won't generate enough heat to outdo the loss rate. So the smallest practical size we figure is these units that are on the order of some tens of kilowatt hours. So we're building those individual cells. They're 4-inch square, and eventually we'll go to 8-inch square. But even an 8-inch square one with proper insulation wouldn't be able to sustain itself. It'll lose too much heat. But if you put a collection of them together so that the half width is on the order of about a half a meter, so about a meter across, you imagine something about a cubic meter, that will sustain itself. So, we're not thinking about getting down to the form factor of a telephone. It can't. And besides, it's elevated temperature. You can't use it for personal electronics anyways. If you put it in a car, it's fine because it's sequestered.
Thank you.
Another question. What are you thinking about the first applications for this? You mentioned it's not great, may not be, frequency regulation may not be the first application. Are you thinking renewable integration? What are the other sorts of applications that you're thinking about?
Yeah, so we're looking for the most costly, the highest pain points. So I'll give you a couple of examples. One is Hawaii. Hawaii has the most expensive electricity between Hawaii and Alaska. Hawaii has boatloads of sun, boatloads of wind, but they're intermittent and so on. If they put these batteries in, their costs would actually come down, their carbon footprint would come down, and they would win-win-win. So that's one example. Another example is it's called a transmission line deferral. In New York City, the demand for electricity keeps going up because of the servers in the financial district. And there's plenty of electricity in the New York area, but not on the island of Manhattan. And we're fast coming up in about depends whose forecast you believe, but certainly within several years' time, where in the peak demand times, the demand will exceed the capabilities of the transmission lines, which means the electricity is there, but you can't ship it. And that, I don't think Wall Street's going to take kindly to rolling blackouts and things like that. And that's one place where you can't start erecting a whole bunch of hydrocarbon-fired peaking units. So that's one. And one of the spurs, I can't remember if it's to Queens or Brooklyn, but it is now over demand. And the estimate is $1 billion to put in a second transmission line. So everybody's standing, looking at each other, saying, who's going to put down the $1 billion and ultimately give it to the ratepayers? That's a great example where if you had batteries in the wee hours of the morning when the demand is low, you just continue to send electricity through the lines, store the charge, store it in the basement of skyscrapers, and then in the middle of the day you pull it out. So if you look at the Electricity Storage Association, there are about 17 different uses for storage. Load leveling, load following, peak shifting, frequency regulation, spinning reserves, non-spinning reserves. And each has its own duty cycle, its own electrical characteristics, and its own price point. And if I can get a given installation to operate in multiple markets, then that's advantageous too. And where it gets really difficult You see, right now, they're using the big sky approach. The grid is big and it's interconnected, and so if there's a little bit too much supply over here, maybe we can sort of balance it with something a couple of 100 miles away. But if you get these sort of off-grid microgrids, like the places in Alaska that have wind that 70% of the time is being spilled. Because if the supply exceeds the demand, you'll blow all the circuits. So they just feather the blades. Because there's no place to run, no place to hide. It's too small an operation, and if the demand and supply get out of balance, you're shipping dirty electricity, and the public won't put up with dirty electricity. I'm sure most of you have been abroad where you couldn't drink the water out of the faucet, so you know how to think. But has any of you been to a place where you were afraid to plug in your device? Huh? That's different. That's very different. Imagine bringing that to the United States. Because we have renewable energy. So anyways, the answer, it's a long answer to your question. It's not a single market. We have to understand where the right place is.
I own a solar light company. Do you see a fit for this in solar lighting where you have 4 to 5 hours, let's say, a charge and 12 to 15 hours worth of discharge?
Sure.
Could you make them small enough, I guess, the $1 million question, to make them work together where they'd fit?
Well, right now with the technology that we're working with, I think the smallest practical size would be about the size of a large refrigerator, which would be probably on the order of 10 kilowatt hours. So it wouldn't be a unit where you'd put that with the light, so you're generating and storing it. It can't be a fine grain to that extent. But it would be fine grain from a grid perspective. Because you can imagine if every homeowner was a generator and they could all communicate. You know, in Superstorm Sandy, there were communities on the Jersey Shore that had solar panels on their roofs after the storm, and they couldn't have access to the electricity because it was mandated to go from the roof to the grid and then back, and the grid was down. Why? Because the grid operators say they need to know if the electricity is being sold or not. I bet you can develop a device that can tell you that. So this is just a really, really antiquated system that needs a good remake. But, you know, some of it is regulatory and some of it is just inertia. But Phil Giudice, when he was Undersecretary of Energy in Massachusetts, came to Texas once to talk to a bunch of electricity generators. And he was talking about modernizations and stabilization and removing uncertainty and so on. He could tell that body language in the room wasn't really responding very well. And finally, one of the guys says, we love chaos. He says, when there's disruptions in the electrical supply, it leads to pricing spikes. So you know, this is what you're up against.
We have time for 2 more questions, and then we're going to have to set it up.
What are the hazmat implications? And let me give you a little bit of context. When Tropical Storm Allison blew through here, it weakened the wall of the Buffalo Bayou such that it invaded the tunnel system in downtown Houston. One of the lessons that we learned from that is when it hit the Pennzoil building, it flooded the underground generator space. I believe they had an oil-fired generator. It became a hazmat situation because of all the toxins that now were in the water, et cetera. If you were talking about putting this technology in the bottom of a skyscraper, which sounds brilliant, what would happen if it was, say, flooded by a Sandy or an Allison, where the seawater came in and flooded the area?
So the liquid metal turns into solid metal, so you'll have some ingots sitting right there. It doesn't leak. You know, it's like California, going back to the Aaron Brockovich episode, there was an attempt to ban chromium in all forms in California. Now, I was thinking, you're going to have to clean out your kitchen drawer of all the flatware because it's got stainless steel and that's got chromium in it. It's got elemental chromium. So elemental lead, elemental antimony, elemental lithium, it's fine. The salt, yeah, the salt could dissolve in water, but it's hardly hazmat. So I think it's okay. Because again, it turns into solid. And you know, I thought where you were going to go with this is, what happens at end of life? People ask me that. So now what are you going to do? You've got a big disposal problem. Well, the steel can, we'll go back to the steel recycling mill. We'll send it up to Chaparral Steel in Midlothian, Texas. And the contents will go into a new battery because you're just going to keep using it. There is no end-of-life disposal. So I'm sorry. You know, people ask me, okay, what's wrong with this? And I'm going, I'll try to come up with something that's really bad. Think of something that's it's not easy to dance to. It's people ask me, you know, can children play with this? Is it edible? That's what Colbert asked me. Is it edible?
Professor, you talked about a lot of the inefficiencies with the grid system that I don't think all of us exactly were aware of, but we knew about peak pricing, peak power type issues. But one of the fellows at the outset, the NRG gentleman, talked about, you know, essentially we've got the same grid system that Edison started out with in the 1880s. And if you think about it, an analogy, everything increasingly has gone to a distributed mode. I think about the mainframe IBM computers after the war. Then you went to mini computers, microcomputers, PCs, laptops. Now it's basically down to an iPhone level. So everything seems to be getting more and more distributed in more and more industries, except for the power industry. So I'm asking you, looking ahead into the future, do you anticipate that we're going to see the end of the centralized power system and the creation of a new technology whereby something the equivalent of maybe your air conditioning condenser, everybody at a home and at a business would have their own self-contained power system that would create essentially their power, and maybe they just have to replace like a cell of some sort that generates it? Well, you know, in other words, there would be no grid system in the future. Do you anticipate that in the next, you know, few decades ahead?
I think we could have a mixed system. But, I mean, each of us doesn't think twice about having his or her own furnace in the house. You know, you got an energy supply and you consume it, whether it's gas or oil, or some people even have electric heat, whatever. But the electric, of course, comes through the grid. But you've got your own tank and so on and so on. So, but you could go to that. But I think for congested areas, you know, you see one of the big trends that's occurring is mega cities. The population is becoming increasingly urbanized and into greater and greater concentrations of people. And I don't know enough about just, if you get a concentration of people beyond a certain density, whether there's enough capability in terms of solar and wind and so on that even, you know, if you've got people living in a high rise, that they can generate enough electricity. So I think there's always going to be room for some kind of grid. But I do think that we don't need to be stringing wires from a centralized power generating facility to every remote farmhouse in the country. I think it's possible to decentralize. And if it's decentralized, it's going to be more robust. So, but you know, it's one of these, if I asked you in 1980, so let's get a lawyer in here and ask, how would you write the contract for a service that would give you data over, like wirelessly? So you'd be able to take data wirelessly. Everybody looking at you saying, what are you talking about? You're crazy. So no one's ever asked these questions about, you know, what is the grid capable of, and to what extent can we have a system that's hybridized, that's a combination of individuals, distributed and centralized. I don't know. But boy, with what we have in terms of computational capability today, it should be obvious. It should be obvious. And we're not talking about, putting, great big variacs in places. We're talking about, little switches and so on. It could be so simple. But no one's asking those questions. Or maybe they are and they don't want to hear the answers. I don't know. I got enough to do, I got to make this thing work.
Okay, let's thank Dr. Sadoway again. Fantastic presentation. I'd like to do two things before we close. Rosalind, could you, or Yasmin, could you please come up? And we've got a presentation for you. And the second thing I want to announce is MIT alumni. If you want to come up here after we finish, we'll get a picture with you and Donald Sadoway. And then our sponsors, if you could do the same, we'll get you a picture of you with Donald Sadoway. So anyway.
Yeah, Professor Sadoway, would you come up, please? Come up, Professor Sadoway, on behalf of the MIT Club of South Texas and the MIT Enterprise Forum, I want to give you this wonderful gift, and thank you so much for coming to be part of our event tonight. Thank you. We do want him to open it. This is it's a battery. No.
We can ship it home for you.
You can take it. A little memento of your visit to Texas. All right. Awesome. Thank you so much.
My pleasure.
All right. Just in closing remarks, I hope you enjoyed the show as much as I did. This was a wonderful lecture. There are things I heard tonight that I had not heard before, and I hope that you benefited from what Professor Sadoway said about some of the new developments for energy storage. Pretty amazing. One last thing on sponsorship. If you liked what you saw here tonight, your name was not up on the sponsors list. I encourage you to think about becoming a sponsor for the MIT Enterprise Forum or joining as a member. So, with all that, thank you very much for coming. Please drive home carefully, and thank you. And people, alumni, and sponsors, please come up here for pictures. Okay, thank you.